from Liverpool, who's going to tell us about Yukawa couplings in F-theory compactifications.
Okay, thank you very much for the invitation. So what I'm going to talk today about a small issue in F-theory compactifications. I mean, F-theory compactification has many directions, but I'm only going to touch this one. And this is based a bit older result that I had with Taizan Batari et al. Then I'm going to emphasize on two papers which appeared last year. The first one pointed out some big issues, big problems with the Yukawa couplings from F-theory compactification. The second paper more or less solved them. And I'm going to discuss also about some work which is going to appear soon. So, as we are going to have a conference here in 2 weeks' time, in 2012, string phenomenology covers many directions, and most of the people in the room are the pioneers of these directions. So, okay, the first one is free fermionic models, orbifold models of heterotic string compactification, vector bundles in heterotic string compactification, intersecting D-branes and F-theory phenomenology. Yeah. So this was.
You miss someone.
Probably, I know. Sorry. Largest dimensions. Sorry.
But different singularities.
Well, I mean, this is. I consider them to be like T-dual to intersecting branes.
What about rational CFTs and Gepler models?
Oh, I was different.
Okay, I mean, this is, I don't know, I relate them to free fermionic models, I don't know.
Thank you.
I mean, sorry, I apologize, there are, of course, there are other. So, what I'm going to discuss today, I mean, I'm not going to discuss about the first four, I'm going to discuss about a small issue in F-theory phenomenology. So, I'm not touching any other aspects, so only the issue of the Yukawa couplings in F-theory phenomenology. Yeah? In order to understand why this issue appears here, let me revise the story which led to consider this F-theory approach. So there are many ways to engineer standard models. One of the most popular is the intersecting branes in type 2A, type 2B, which of course is T-dual to some branes and singularities. So about 12 years. Well, I mean, you can have non-geometric fluxics, or I mean, eventually, you can make some. Good. So matter arises from intersection of the branes. So the standard model itself is not difficult to build. Now the question is, how do we build gut theory here? And we have three possibilities, SU5, SO10, E6. And the question is, can you use only perturbative open strings to do that? And the answer is unfortunately no, for various reasons. So let's take first E6. The problem with E6 is that you cannot build E6 with only D-brane configuration, local D-branes. For example, you can put two types of D7 branes together, but then the theory is non-local, so it's it's hard to understand it in type 2B. The second possibility would be SO10. SO10, you can put 5 branes on top of each other, put an orientifold, you get SO10. That wouldn't be difficult. Then you can put some more stacks of branes or put some singularities, then you get SO10 with some flavors. The problem here is that the quarks and leptons sit in the 16 spinor representation, which cannot be obtained in brane configurations. Yeah. Otherwise, we would be, I mean, we could get very interesting results like Zyberg duality for SO10 with 16 representation and other things, but unfortunately, this is not possible. The third possibility would be to have SU5. Now, SU5, it's even simpler to obtain with D-branes. Matter content consists of fundamental matter. Then you can have anti-symmetric field by putting some orientifold and various stacks of branes, and by the projection you can get symmetric and anti-symmetric representations. But SU5, so SU5 in principle you would get all the matter, all the gauge fields. The problem is that it doesn't exclude rapid proton decay and cannot describe the up-type quark Yukawa couplings. So for the point A, in what sense does not exclude rapid proton decay? In the sense that you can have this term, which is masses for quarks and leptons, but then you don't know how to say that this is allowed and the second one is not allowed, which would imply proton decay. So the only way to do that is to have two 5-bar representation for SU5, and as I'm going to say a bit in a minute, then you have to go to embed SU5 in a higher group, yeah? And the other issue is the up-type Yukawa coupling, which involves this epsilon, which cannot be realized in brane configuration, only non-perturbatively, yeah? So these two reasons imply that this SU5 has to be embedded in a higher group, and the minimal choice to get the epsilon tensor is to be embedded in E6. And for the proton decay, the minimal choice is to embed it into an E7, where E7 is broken into SU5 by having these two U1s, and now two 5-bars with various U1 charges can be distinguished between themselves, so you can distinguish between the H-bar 5-bar and the 5-bar, yeah? So E7 is the minimal underlying symmetry which has both up-type Yukawa and no proton decay, okay? So of course this E7 can then be embedded into a E8 group, so this is why initially about 6 years ago the first proposal was that these GOT groups can be embedded into heterotic strings, which was better understood at the time. And then some dualities with F theory led to some conjectures in F theory, which unfortunately, then were overseen by the proposal of Waffa and collaborator. Yeah. So this was the initial proposal that in heterotic strings you can embed this SU5 into E8. Yeah. Similar story for SO10. Now we need to break E8 to SU5 or SO10. In F theory, there are several possibilities to get to SU5. So in F theory, okay, I'm going to discuss in some more detail. In F theory, one has some elliptical fibration with some singularities, which can be A4, and then it can be more than A4. So if you have E6 singularity in the elliptical fibration and they resolve it to A4, then this is when you get the up-type Yukawa couplings. For this part, you will get the down-type Yukawa couplings, and from here you don't get any Yukawa couplings. The same for SO10, you resolve E7 to D5, which is SO10 or D7 or A7. Yeah. So this is in F theory. You just look at the elliptical fibration and you partially resolve the singularity. The initial discussion was for the heterotic E8 cross E8, where you can get SU5 by turning on a vector bundle SU5, or you can turn on SU4 vector bundle and to get SO10. Yeah. So heterotic string was important because some aspects of it were exactly mapped into F theory, and because heterotic, of course, it's easier to understand, at least in a global picture, because F theory it's easy to understand in a local picture that I'm going to discuss in a minute. But this doesn't mean that we have a good understanding of F theory in the global picture, except in some cases. So this is why the heterotic string was developed first. So when we turn off these vector bundles, there is a correspondence between the representation of the vector bundle and those of the unbroken SU5. For example, for the fundamental of this the vector space V, the 5 of the vector bundle SU5, it corresponds to the 10 of SU5 GOT. For the V star corresponds 10 bar, and now if you take the bundle W square of V, this corresponds 5 bar, and this, yeah. So this was built by Wheaton, Morgan, and Friedman about 15 years ago, and for the bundle W square of V, we built it in about 3 years ago with some mathematician. So okay, this is quite well understood how to build this in heterotic strings. So as I said, heterotic string is important because it gives hints on F theory, yeah? Because heterotic on T2 and F theory on case 3 are related by duality, yeah? So the first hint of how to deal with F-theory was to consider the heterotic strings compactified on an elliptically fiber Calabi-Yau threefold. And the specific example is for the rank 5 bundles V, and for this the elliptical fibration has this form where U and V are local coordinates on the base of the Calabi-Yau. So it has this specific form. This has been given by Friedman, Morgan, and Witten. And what is important here is that if you say, okay, we don't want to work with the full base, 4-dimensional base B2, but we want to restrict ourselves to some 2-dimensional locus on the base, then we can do it by either putting A5 to 0 or by putting some coefficient P5 to 0. Yeah? Now, when A5 is 0, we get exactly the 5 of the SU5. So this is the 5 of the SU5 lives at the locus A5 equals 0, and the 10 representation lives when P5 equals to 0. Yeah? Now, in order to get the Yukawa couplings, you need to get some intersection between, some coupling between this fundamental representation and the 10 representation. So there are two types of Yukawa coupling which are obtained when A5 equal A4 equals 0 and A5 equal A3 equals 0. Yeah? So this is all heterotic string result. And these results were mapped one-to-one into F-theory. Yeah? So this is, I just mentioned a bit about heterotic string to more or less give some historical detail that firstly things were derived in heterotic string, then they were mapped into F-theory, and in F-theory they were then reinterpreted as in terms of branes and wrap branes on 4 cycles. Yeah, good. So now let's go to F-theory. In F-theory, so heterotic string was compactified on a Calabi-Yau threefold, so going from 10 to 4. In F-theory, we go from 12 to 4. So we have a T2 fibration over, I'll use various notations. So a T2 fibration over a 6-dimensional manifold. So this is an 8-dimensional manifold. And in order to get some gauge groups, you just wrap D7 branes on 4 cycles inside this M6. Yeah. So you have T2 over M6, and then you have 4 cycles inside M6. Yeah. Now, what happens when these D7 branes are wrapped there? There is a degeneration of the fibers, and this is exactly the geometrical representation of the presence of the D7 branes. Yeah. So F-theory contains all the information about the D7 branes, and their back reaction means that their influence on tau and the other aspects of the theory. Yeah. Good. So now, okay, so this is instead of M6, now I denote here by B3. So we have X, it's an elliptical fibration over B3. We assume that X is given by the Weierstrass equation. So the singularities of the fiber is telling us where the D7 branes are present. So if you have an AN singularity, means that you have stacks of D7 branes of the same PQ type. If you have a DN singularity, you have stacks of D7 branes and O7 planes. If you have EN singularity, you have overlaps of different 7 branes. Yeah. So the gauge fields, they live on D7 branes, or D7 wrapped on the divisor. Yeah. Good. So this is the same as the vector bundle in the heterotic case. Yeah, which was over the full. Over the base of the 6-dimensional manifold. Yeah, so the gauge field lives on the 4-dimensional manifold. Yeah. Now, if you want to restrict to matter fields, then they lived in a 2-dimensional manifold in a heterotic string. In F-theory, they are going to live again in a 2-dimensional manifold, and 2-dimension inside 6-dimension, it's a codimension to surface. And this codimension to surface is an intersection of 2 or more divisors. Yeah?
This is not a general statement. In the heterotic string, you have much more general possibilities than just having matter fields on codimension 2. You can have matter fields in the bulk in 10 dimensions.
Yeah, that's true.
It's related to your very specific.
Yeah, I mean to my model, to the model that I consider. No, I mean I'm just okay. So this is just the vector bundle construction. Yeah, of course it's not. I mean I don't say this is the more general. I mean this is the specific Friedman-Morgan-Witten model. Yeah. So when you have elliptic fibration and then you restrict, four gauge fields 4, matter fields 2, Yukawa coupling 0. Yeah. So I mean this F theory models were tailor-built to be dual to that heterotic string of Friedman-Morgan-Witten. I mean, it doesn't describe any heterotic string. This is just specific place in the model. Yeah, okay. So, this doesn't tell us much about F theory. Now, one development of 4 years ago was the introduction of this local F theory phenomenology by Waffa and collaborators Donaghy and Weinhold. So local, this means local, so it's not, I mean, it only describes a very, very particular case of models. And why do we care about this? Because this is borrowing some concepts from topological field theories. They described an 8-dimensional super Yang-Mills compactified on these divisors, on S, which is a compact Kähler space. So many aspects of the gauge theory for these theories depend only on the geometry of X around S. So, okay, unfortunately, this doesn't tell us too much about the real compactification, but as a toy model, we can consider them. These local F theory models. So to study the F theory on X, reduce to the study of 8-dimensional field on S times Minkowski. So matter multiplets will only see the geometry along codimension 2, locus of B3, and the Yukawa couplings are obtained for codimension 3 loci of B3. So this, what does it mean? This, if you take the equations of motion and you solve, then you'll see that there are some Gaussian distribution around the position of this codimension 2 locus, and this one are also forced to live there. So that means that this is a very simple model, and I mean it's not real, but it's a simple model where we can look about some aspects of the theory. So having these 7 branes in 10 dimensions means that there are 2 directions which are orthogonal to the 7 branes. And let's consider this field phi 1, 2 as the transverse fluctuation of D7 branes in type 2B. So this field is a field which lives in this, it's a scalar field of this 8-dimensional super Yang-Mills. So giving expectation values, when the expectation values of phi are 0, means all the D branes are on top of each other. When we start giving various expectation values to phi, then the D7 branes are distributed on the direction U1 and U2, where U1 and U2 are directions of S. Okay? So now I'm going to start, so as I said, the Yukawa couplings are obtained for the rank 2 deformation of some singularities, and I'm going to point out some problems, even in this very simple model, which showed that this interpretation is not 100% correct or 100% understood. And then I'm going to go forward and show that indeed there are things that we still have to understand and to explain. So let's consider a very simple model. Let's before going to the God group, let's consider just n plus 1 singularity. So n plus 1 singularity would be y squared is x squared plus z to the n plus 1, n plus 2. And let's consider a deformation of this singularity, writing this z to the n multiplied by z squared plus s1 z plus s2, where s1 and s2 are not simple parameters, but they depend on u1 and u2, which are the coordinates of the non-compact base S. Good. So we get a family of surface singularity n plus 1 over S, which is deformed to n minus 1, by varying S1 and S2. Good. Now we can map this geometry deformation into the field theory, and we can take the field that I mentioned before, this phi 1, 2, which represents the transverse fluctuation of the D7 branes, and we can take it to have the diagonal values to be n zeros and tau n plus 1 and tau n plus 2. Tau n plus 1, tau n plus 2 are directly related to S1 and S2 here, yeah? Now, it really matters on how S1 and S2 depend on U1 and U2. If S1 and S2 are given by this formula, then you can say that tau n plus 1 is this, and you see that tau n plus 1 is this, tau n plus 2 is this, yeah? So this means just simple, you have n plus 1 branes on top of each other, and you rotate two of them, so they are both at U1, all of them are U1 equal U2 equal 0, and then you rotate them, one to be along U1 and the other one to be along U2. And what you get is that SUN plus 2 theory goes into SUN plus some bifundamentals between the branes which are single branes, which are this, plus some scalar field which is not charged under the SUN. Yeah. So this is the simple case, and this is just because of this choice of S1 and S2 in the deformation of the singularity. More complicated and more interesting case is when you choose other case, S1 and S2, S1 to be U1, S2 to be U2. In this case, the field phi 1 has the two entries which are non-zero, given by this and given by this. And this is the decomposition. SUN plus 2 goes into SUN plus SU2 plus 2n plus 2n bar. Yeah. So you see here that this has a much more difficult interpretation in terms of branes, and the vevs of the field phi 1, 2, they just become -1 of their selves when you go around this locus. Yeah. So this is related to some results of Morrison and Katz, which says that more in this language, it says that the SUN plus 2 adjoint fields are glued to themselves after twisting by a Weil group of SU2. Yeah, and this Weil group of SU2 is just the -1. Yeah. So this is not a simple theory of fields in SUN plus 2. Yeah, which already tells us that just considering these eight-dimensional field theories and wanting to obtain going from a group with a rank n plus 2 to a group with a rank n, there are some difficulties for specific choices of the deformation of the singularity. Yeah. So this was for a toy model. This was for the deformation of the n plus 1 singularity. Now we can apply the same thing for SU5 F theory compactification. So before considering the deformation, let's discuss a bit about it. So this is the Weierstrass model for the SU5 singularity. X and Y are the coordinates of the elliptic fiber, and Z here is the normal to the divisor S where gut gauge group lives. Yeah, and A0, 2, 3, 4, 5 are functions of the local coordinates of S. Okay, so what can we say about this model? We have a discriminant, and we see that delta is 0 when Z equals 0, and this is the locus of the SU5 gut gauge fields. And then we have two matter curves. One of them is A5 equals 0, which is the 10 plus 10 bar representation, and the second one is at P5 equals 0, which is 5 plus 5 bar representation. Yeah, so these results were firstly obtained by a direct map from heterotic string, and remember I just mentioned before that A5 equals 0 and P5 equals 0 correspond to the various representation of SU5. Yeah. Now when A5 is 0, singularity is enhanced from A4 to D5. and Hahn singularity is A5 along P5 equals 0, so P5, A4 goes to A5. And this you can see by looking at delta, which is quite simple. Now, you can have on the A5 curve, so on the A5 curve, remember, it's exactly where the 10 and 10 bar representation are localized. You can see that you have two types of 0. One, when is the common 0 of A4 and A5, so A4 equal A5 equals 0, and the type, I mean, this notation with D is just borrowed from the heterotic string when we define the singularity, so I mean, it doesn't matter if it's B or D. It's a common 0 of A5 and A3. On the other hand, so this is where the 10s are located. On the other hand, where the P5 are located, you have other type of singularities. For example, when P5 and R5 is 0, but A5 is non-zero, yeah? So this way, you can get the deformation from A4 to E6, D6, and A6, yeah? In terms of the field theory, you need to consider these local models with E6, SO12, or SU7 gauge groups. And when I set the field phi here, so you have to consider the E6, SO12, or SU7, and then you give an expectation value to this field phi in order to reduce it to SU5. Yep. So the model that I'm interested is the one when E6 goes into A4, which is the case when A5 equal A4 equals 0. And why I'm interested in this model, because this is where the up-type Yukawa appears. And this is the reason why we went through all this procedure. Otherwise, if up-type Yukawa would appear in type 2b, then we wouldn't need to go to F theory. But because it doesn't, then we need to consider this kind of deformation. And let me just go through a little detail of this. So E6 going into A4. At this point, we have this Yukawa couplings. So now, which way did we consider this kind of deformation? So we want to consider E6 going into A4 in the following sense. So if you take this singularity, y square equal x cubed, and then you put all the epsilon to 0, you get y square equal x cubed plus z to the 4 over 4. This is exactly the E6 singularity. Now, in order to smoothen it out, we added some other terms which contain these epsilons. So there are 6 epsilons, and these are, if all the epsilons are non-zero, this means that the E6 singularity is completely resolved. If some of them are 0, some of them are non-zero, you still get the singularity, but which is smoother than E6. Yeah? E2, E5, and all the epsilons here are functions of the U1 and U2, which are the coordinates of S. Yeah? Now, we knew the result from Katz-Morrison, which told us that the formation of the E6 singularity with 6 complex number Ti, which are the basis in the Cartan subalgebra of E6. Yeah? So these epsilons that appear here are going to be all functions of the basis of the Cartan subalgebra of the E6. So I'm not going to go into full details here. Okay, so what we wanted to do was the following. We wanted to take this kind of deformation. Then we took the SU5 singularity, and we wanted to see in what limit of the SU5 singularity this deformation of the E6 maps into that singularity. Yeah. So we took the SU5. SU5 contains this coordinates x, y, z in the elliptical fiber, and then we made a rescaling. And after this rescaling, we got this. Okay, there is something missing there. We got this elliptic fiber for the deformed SU5, and then we went back to E6 and we chose this Cartan subalgebra, which has one term with tau as 5 terms with tau and 1 term with tau plus 3 sigma. And we wanted to map this tau and sigma into the values of AIs. And the deformation parameter correspond to this kind of this relation 12 here. Yeah. So if you make this choice, if you make this identification, then the deformation of E6 goes into this limit of the SU5. Yeah. Good. Now this sigma and tau, as I said, they are functions of the coordinates of the base S. So we can have another choices here. So one is sigma, for example, it's U1, tau is U2, in which case we don't have any problem. But the more general case is when sigma and tau are given by these relations, in which case A4 tilde and A5 tilde are now the set of coordinates on S, when sigma and tau will have this form. Yeah. So what is interesting here is that again the problem of the square roots appear. So we have a field theory with some expectation value for some field which has these square roots here, and in order to resolve this issue we introduce some covering surface of which more or less got rid of this square root. But you know, it was not completely clear why we needed to do that for this case. Yeah. So even though the problem is somehow solved, means that we could see the deformation of the E6 into A4 or E6 to SU5, and by introducing this covering surface C, it is not clear why do we need to do it, and what is the goal of doing it. Yeah. Good. So this was this discussion. Okay, so this is for the E6. Now if you consider the other singularity here, which is the common zero of A5 and A3, then you get something else, which is you get the down type Yukawa coupling. So so this is the D6. You get a D6 singularity or SO12 group, and this SO12 group is used to describe the local geometry of the new codimension 3 singularity. Yeah, so the discussion goes the same. I'm not going to enter into detail. So what is the problem here is that, so I mean, this, if these models were the ultimate one, then we'd still be happy. But the problem is that these are only local, and they determine the local behavior of zero mode wave function and calculate Yukawa couplings located as codimension 3 singularities. Yeah. Now they imply that there is a non-compact base space S, and they cover only a local region. Yeah. How can we extend this region? Yeah. So now the question is this everything we can do, or we can do more than that? So there are two extensions. The first one is called semi-local, which is still more or less local, but it can be extended a little bit. And the second one is called the global one, which was mostly developed by Sakura, Schaeffer, Nameki, and Marsano and Saulina. So firstly, let me say some brief words about semi-local, even though I'm not going to cover in what follows. So to describe the semi-local limit, one borrows the notion of spectral surfaces from heterotic strings. So what is the spectral surface here? We can get to there if you ask the question, what can describe a collection of a field phi, so the scalar field phi that I mentioned before, and the vector bundles on this non-compact base S? Well, they are described by V and phi. So this is the vector bundle, this is the phi, and this is called the Higgs bundle in the literature. Yeah. So for the heterotic strings, we only had V because we lived in 10 dimensions. Now, because we live in 8 dimensions, we also have to describe in terms of phi. Yeah. Now, what was good about it was that everything which was known about compactification of heterotic strings, where we only need to build this vector bundle, was quite easily generalized to the Higgs bundle. I mean, we had the mathematical tools already there again by Donaghy. So this is why Donaghy and Weinhold could present very nicely the results. So what does it mean to have this Higgs bundle? Means to solve this kind of equations. This is the field phi. This is the vector bundle. So we have to solve this equation, and these are called the Hitchin equation for the Higgs bundle. Yeah. So if one solves this, then one generalized. So instead of just having phi as I did before, one also introduces f, and this is the so-called semi-local region, where you don't care only about phi, but you also care about f. Yeah. So also by doing this, you can get a very nice. I mean, you can generalize the duality between F theory and heterotic strings. But the only thing that you need to introduce is this local Ford flux, which corresponds to some specific quantity in the heterotic strings. So it's very important to introduce this. And in F theory, the Ford flux is related to the chirality of the fields. Yeah? So there were many developments obtained by many people, among them Blumenhagen and collaborators. Now, there was a question which was asked last year. Do we really expect to get singular spaces from singular spaces? So everything that I discussed up to here implied that if you start with a D6 singularity, you resolve it, you get the A4 singularity. Yeah? And this is the Kodaira classification of the singularity. So you get a nice Kodaira type singularity into Kodaira type singularity. Yeah? Now, if this is true, then also by resolving here and resolving here, we should map into each other. Yeah? So last year there were two approaches, one by Essole and Yao, and the other one a bit later by Marsano and Schaffer-Nameki, which consider this kind of mapping. Also the papers by Morrison and Taylor, which did also many other things, but then also cover partially this discussion, but not completely. I mean, Essole is the one who covered completely. So they ask what happens if you have an explicit desingularization. Yeah. So let's consider now a Weierstrass model, which is a 8-dimensional manifold elliptically fibered over a 6-dimensional manifold. The fiber is this. X, Y, Z are projective coordinates on a P2. And let's take now the specific case when we want to write this elliptically fibration around a divisor which has this I5 singular fiber, which means this corresponds to SU5. Now, if you take this choice, so you want to write it around W equals 0, means that you can expand A1, A2, A3, and A6, A4 and A6 in terms of W, and this is the equation that you encounter. So this is this equation. This is a singular curve at x equal y equal W equals 0. You can always choose Z equal 1 because you live in a P2, so you can restrict to the Z equal 1. So what do you get here? This is a singular curve, and you just need to resolve it the usual way. But you know, in the conifold theories, or resolved conifold or orbifold theories, one usually introduces P1, resolve the P1. Here, because we are in 6 dimension, then we introduce a P2. So, but you know, the rest of the discussion is the same. So we have the x equal y equal w singularity. We need to blow it up. We introduce this homogeneous coordinate u1, u2, u3 over p2, and then you know we just put a p2 at the singular point. We get 3 patches corresponding to the points where u1, u2, and u3 are non-zero. So just before, when w equals 0, we already had a curve here, written just in terms of x and y coordinates. So we will get these curves in the resolutions. Now the first two resolutions are smooth, the third one is still singular. That means we have to still resolve it, and we put another P2 here, given by these equations, and we get another 3 patches, and we get another 2 curves, C2 plus and C2 minus. Yeah, so we have a C0 that we started with, we have C1 plus, we have C1 minus, we have C2 plus, we have C2 minus. You can you can study the intersection between these curves, and then you see that this is exactly reconstructing the Dinky diagram for the extended A4. Yeah, so we have A4 should have four cycles, which is exactly 0, 1 plus, 1 minus, 2 plus, 2 minus. Yeah, good. So this is just studying the case when W equals 0. Yeah, so this is for the gauge fields. Now, if you want to do more than that, then you have to go to the codimension 2, which in this case is beta 4 equals 0, or beta 5 equals 0, beta 4 equals 0. So again, the singularity is this one here, which now contains these betas. It's the same as A I denoted before. And codimensions 3 singularities when you have beta 5 equal beta 3 equals 0. Yeah. Now, how to think about this? So, in order to see how to resolve the singularities in codimension 2 and codimension 3, let's just remember briefly about the conifold singularity, which is xy minus uv equals 0. And there are two possibilities. There is a vanishing P1 here. And how to smoothen it out? You can either put a P1 at the singular point, which has this equation, or you put an S3, which is xy minus uv. This is the equal here, sorry. Xy minus uv equal epsilon. Yeah. So doing either A or B, you smooth out the conifold singularity. Yeah. Now epsilon here plays the role of a complex structure deformation. Yeah. If you turn off the complex structure deformation, you go back to the singular conifold. Yeah. Now our geometry here has this coefficient beta 5, beta 3, beta 2, beta 4, and beta 0. Yeah? Not all of them are important, but beta 5, beta 3, and beta 4 are important, and they all play the role of epsilon. Yeah? Which means that if you have this curve here, and if you put beta 5 to 0, then beta 5 is like a complex deformation, beta 3 is like a complex deformation, beta 4 is like a complex deformation. So the same as in the case of the conifold, you expect to get a harsher singularity, a more singular space. So indeed, if you put this to 0, then instead of getting the conifold singularity, so the conifold singularity that you get from xy minus uv equal epsilon, take epsilon to 0, in this case, you get another type of singularity, but instead of being one equation inside C4, you get one equation inside C5, and this is the so-called binomial geometry. So, if you put beta 5 equals 0, in this case, some of the cycles that I mentioned before come on top of each other. So, that means you need more cycles to really resolve the singularity. If you put beta 4 equals 0, then you need another cycles come on top of each other, so you need another extra P1 cycle to smoothen out. Yeah, so beta 5 equals 0 means that you need another P1, and now if you take the intersection between the new P1 and the older P1, so all these C1 plus minus, C2 plus minus 2 and C0 are all P1s, so the intersection between the new P1 and all the 5 P1s that were before would give rise to the D5 tilde diagram. Yeah, beta 4 equals 0, you need an extra P1, you smoothen out and you get the A5 diagram. Yeah, so this kind of worked. Yeah, so if it were only for the matter, so remember this is exactly where the A5 and where the 10 and the 5 of the SU5 live, so this should have been okay. But now the problem was that if you take more complex deformation to 0, so you make the singularity even stronger, then you need extra P1s, And if you put the extra p1s and you consider the intersection between these extra p1s and the older ones, you do not get the D6 or E6. And especially you don't, I mean, D6 you almost get up to some coefficients in the Dynkin diagram, but this one here you don't get. Yeah. So the question was, does it mean that you know, the E6 cannot be obtained from F theory? Because, you know, as I said, E6 was the great achievement because it gave us the epsilon, the antisymmetric epsilon. So would it mean that it's doomed? So the answer was then in a nice paper by Marsano and Schaeffer-Nameki, which proposed the following. Yeah. So they said, okay, this just tells us that you do not get from a singular space to a singular space by deforming this elliptic fibration. Yeah. But what you can do is that instead of increasing the number of the roots, so instead of enlarging the root lattice, one should consider the SU5 weight lattice. Yeah. Which means that the SU5 roots split above a codimension 2 and the codimension 3 singularities, and this is the split will exactly represent some extra state in the 5 representation or 10 representation. Now, I don't have much time to introduce this global approach. Maybe Sakura can, or maybe she was here or she will be here to give a full detail of what is the global approach. But what I can say is that the coordinates that I introduced before are section of the bundles and are defined, divisors are defined when these sections vanish. Yeah? For example, C naught, Z is a section, so Z equals 0 is the position of C naught. C1 plus, C1 minus, C2 plus, C2 minus represent positions where some other sections vanish. So, you know, the same number of fields, the same number of cycles exist as before, but now it's just that they are defined a bit different in this global approach. So they are defined as intersection of various divisors, and they are denoted by sigma alpha I. So there are 4 of them. See, there were 4 of them here, and then there are 4 of them there. And how do we see that we have an SU5? Is that you consider this the intersection between sigma alpha I and the gauge divisors, and you'll see that you obtain exactly the Cartan matrix of SU5. Yeah, so this implies, so this sigma is 2 dimension, the divisor are 4 dimensions, so 2 times plus 4 is 6, so integrate over the full manifold, you give some number, and this should be just 2 minus 1 and 0. Yeah, good. Now what happens if you take beta 5 equals 0 here? The sigma splits, and then you get this split of the root, which means that, for example, you have the first 3 roots go into themselves, but the second and the fourth root go into something like this. And this is why, how do I know that this number should be here? It's again by considering the intersections of the new sigma alpha i's with the divisor, and we will get these numbers here. Yeah, and this is exactly telling us that at the codimension 2 case there is a field in the 10 representation, but this doesn't mean that we have D5. It's just that it involves the weight of the highest weight of the 10 representation. Yeah, the same for the codimension 2. We take p equals 0. Okay, and codimensions 3, you see some further splitting of the 5 into 2 tens, and this implies a 10-10 5 bar coupling. Yeah. So what we kind of learn from here is that if you give up the idea of trying to go from one singularity to a higher singularity, and you allow the splitting of I mean, in this global picture, you allow the splitting of the roots into weights, then you can still get the coupling. Yeah, so this is exactly what we were after. Yeah, good. Now these constructions, there are some consistency checks. And one of the consistency check is to consider this G flux, which is the non-zero 4 flux, whose integral is n minus n bar. So this should give the chirality of the theory. So now this global 4 flux in the global model, you can take the global model, you take some limits which are similar to what I discussed before when we deformed E6 into A4, and then you map the global 4 flux into this semi-local 4 flux, and the match is indeed perfect for the SU5. Yeah. Now, what is my contribution to this? So recently, I mean, we have considered, instead of starting with SU5, we considered the SO10 groups. The E6 was recently treated by Sakura Nameki and some student. Now, why is SO10 a bit more difficult? I'm going to tell at the end. So, I mean, this meaning that E6 and SU5 are on the same footing, which are means that are a bit simpler than SO10. So the Tate form for the SO10 singularity as z equals 0 is this. And as I discussed before, there are two approaches to deal with deformation of the singularity. One is the Soleil-Yau approach. So this is what we tried first, because I mean we didn't realize that how difficult it would get. So this would mean the SO10 would be deformed into a E6, into E6 D6 for codimension 2, E7 D7 for codimension 3. Now you resolve the singularities the same as before. You get 5 cycles. And now the problem was that once you start putting to 0 some coefficients here, then some of these 5 cycles will go on top of each other, and then you need some extra 2 cycles in order to fully resolve the singularity. Yeah. Now turning these coefficients to 0 and then blowing up turns out to be much more difficult for SO10, and this is because there is a overlap, there is interlace between Keller and complex deformations. I'm not saying it is not possible to do, but for the moment, we kind of gave up because it was not very easy to see how to resolve it. So even to resolve is difficult, let alone, but it is still expected that you won't get E7 and D7 here. At least the E7 is very problematic. Yeah. So this should be the Soleil-Yau. Then one can try the Marsano-Scheffer-Nameki approach, which indeed works well. The same way as we had the splitting of the 10 and the 5 matter fields for the SU5. In this case, we have the splitting of the 16 and 10, the matter fields. So without getting into my detail, so we had this SO10 singularity curve. We need, in this case, we need 3 P2s for the codimension 1, and the further 1 for the codimension 2 and 2 for the codimension 3. Now, even doing these blow-ups, you have 3 plus 1 plus 1. It depends in which order you make them. Yeah, when you go, for example, to the codimension 3 singularity. Yeah. So, in order to get what I said before, the intersection between, if you want to get the Cartan matrix for the SO10, you need to do these blow-ups in a specific order. Otherwise, you don't get it. So, okay, this is another thing that I'm not quite sure why it depends on the order you do the blow-ups. But indeed, it seems that if you do the blow-ups in some specific order and in some specific way, this is when you get the Cartan matrix for SO10, and the same thing appears for A6. Now, if you do this correctly, so if you do the blow-ups correctly and you get the Cartan matrix for SO10, then you see that the splitting for 16 goes like this. So let's say the third root splits like that, and for the 10, the fifth root splits like that. Yeah, and some further splitting exists for the codimension 3. Yeah, so this goes very, very similar to what was done for SU5, except, as I said, that there are some subtleties here on how you do the blowing ups. I didn't present it in full detail, but that require quite a lot of tinkering. Now, what is a bit trickier here is when you want to map the G-flux from the global model to the G-flux from the semi-local model. And why is this? Because, if you consider the quantization of the G-flux, this will, it should be half integer. Then this implies C1 and C1 of S2 or C1 and B3, sorry, they need to be even. And this is true for SU2N, yeah? So this is for the SU2N bundles, which gives either SO10 or, so the SU4 bundle gives SO10. So this condition appears only when you have SU2N bundles, yeah? So this is why I said that SU5, because SU5 contains the SU2N plus 1, E6 contains the SU3, which is SU3. So for E6 and SU5, it doesn't appear this problem, but unfortunately, since that for the SO10, which involves SU4 bundle, you need to impose this extra condition. And we're not very sure exactly what this would mean. Yeah. So in conclusions, F-theory seems to be a good tool to study various aspects of God theories, even though even things that seem to be quite trivial still present problems. And this is just because, we don't have a good understanding. So, I'm not saying this is the best tool. It's a good tool as, any other. Fortunately, mathematics is not very well understood. So, it's going to be trial and error for a while. Needs tweaking. So the tweaking is, as I say here, every time because we don't we don't have a perfect understanding of the mathematics which is involved. So this is why it is the tweaking, because we need to, in my understanding, the problem stands that we need to go from resolving these conifold singularities to resolving or deforming this kind of singularities, and this is not something that has been studied in full detail on how to deform the singularity in the best way, or orbifolds of these singularities. So this is what I mean by tweaking. And also that it seems that in order to get the Yukawa couplings, at least the E6 to SU5 Yukawa coupling, which is contains the epsilon, one needs to go to this global approach, which unfortunately it's even more complicated than the other one. So it requires quite a huge amount of work to maybe just obtain very simple results. So yeah, there is more to be done along this direction. Okay. Thank you very much.
Questions?
Well, I'm somewhat lost. I have a few questions. The first one is that you say when you desingularize these things, that you get problems with the Yukawa coupling. You say this was resolved because you take the SU5 weight lattice instead of the root lattice. Do you have a choice there, or are there still rules to follow, or is it just that you in some way start?
It's. So this is, So
I'm somewhat a bit.
Okay. So here, when you consider this sigmas, and then when you put this beta 5 equals 0, then you resolve it in such a way that you have this kind of splitting. So you just take.
So the problem is when you have a singularity, you resolve it, and you want to go back again, you have no unique solution. Is that what the problem is?
The idea is that more or less, it is,
What Isole and Yao in some way pointed out.
Well, I mean, you know, there is this classification of singularities, right? So the point was that if you start with, let's say, A for singularity, you want to go to E6 singularity, yeah? But this was not, I mean, this is true only for, let's say, codimension 1 singularities, but then here it's applied to codimension 2 singularities. So it was more or less abuse of language, you know. We applied some tricks which were true for the lower dimension manifold to a higher dimension manifold, which was kind of lower, you know. So they pointed out that this is not correct. So,
But you could have started from the higher one, then these problems would have been gone.
yeah, but you know, usually you first start with the gauge group and then you introduce matter and then you introduce the Yukawa couplings. So, more or less you go from...
But the gauge group lives in higher dimensions. This lives in 8 dimensions.
Yeah.
Matter in 6, so you go from higher to lower.
Yeah. So if we lived in 2 dimensions, then if we went from 6, 4, 2, then would be good, you know. But the problem is that we go to, yeah. So I mean, these people, what they did, I mean, Marsano and Sakura, they pointed out that there are some way out of it, you know, just by considering these weights. I think also...
That's the point I didn't, yeah, I agree that they, but I haven't understood the logic, so...
well, the logic...
You can say,
well, the logic is that...
You have 2 ways which,
yeah.
One goes right and one goes wrong. Of course, you can at a given point say, oh, there's
Yeah,
one way, I should forget the other interpretation.
So just, I mean, okay, my understanding is the following, you know. So here you have these sigmas, right? So these are more or less like P1 cycles which resolve the singularity, yeah? So in this case, if you go to a higher singularity, then you have to put another P1 cycle, right? So you had 4 and then you put another one, yeah? So now if you look at the old ones and you compare to the new ones, then 3 of them just go as they are and 1 of them just splits in 2, you know. So I mean, it's true that you have the choice how to do that, you know, but you just do it in such a way that you get this splitting here. I mean, this is partly the why this problem for SO10 is a bit harder, you know, because it's yeah.
So you would say this is resolved by now, or is this?
Yeah, I mean,
But when I go to your conclusion, can you go to the conclusions again, or?
Yeah, sorry.
Because there you say the global approach is more powerful to obtain Yukawa couplings. So you're essentially saying without a global approach, calculation of Yukawa couplings is very tricky.
Yeah. Yeah, I mean, this is my impression.
Rafa has explained all Yukawa couplings in nature correctly already.
The local SUV model.
Well, but as I said, you know, I mean,
This is a bit polemic now.
No, but just 1 second. So, okay, I mean, okay. So as I said, you know, so one of the checks, at least for this G flux, was that G flux for these models maps into the non-local, in the semi-local models. So somehow this would say that, well,
This is another question. So this G flux in F3,
Yeah.
what is that exactly in the heterotic theory?
Yes, but there is another, in heterotic there is another quantity there. You know, when you build a vector bundle, there is a gamma, whatever, and this maps into this flux, yeah.
So there is an exact map.
Yeah, there is, but not flux, it's some quantity there.
In what paper is that explained?
Some curious paper for Curio and Bjorn Andres, some from
Somewhere on page.
Okay, I can show it to you, but
Okay.
it's
No.
unfortunately,
It's a well-defined.
yeah. I mean, unfortunately, you know, these papers are very cryptic, you know. So
Yeah,
it's,
no,
yeah,
yes.
so
No, I guess it is difficult.
yeah, it is defined. Yeah, so it's defined the map between
Yes,
the heterotics. Yeah. So what I'm saying is that, okay, I mean, I don't know how to say it. Is that this G flux computed in the global approach was mapped into something in the semi-local approach. Now, I don't know if this proves that also the semi-local approach is valid, you know, but it's, you know, this was a nice consistency check, you know, so I would say that, you know, this global approach allows a full understanding of the puzzle related to the Yukawa couplings. So, which is not allowed in the semi-local approach. Yeah. So, I mean,
What do you mean by full understanding of the puzzle?
full understanding.
Let me ask. Does it mean that you can find an example where it works, or do you mean that we understand why the top word has a large mass in these models? If I give you a generic model in this class.
Oh, no. Okay. I mean, phenomenology. I don't know. I mean, just.
Well, that's also fit.
No. Oh, sorry. I mean, what I'm saying is that.
Because intersecting brane models, of course, I can also say it needs some tweaking because I have to find an instanton that generates.
So what I'm saying is that I mean, in my understanding, all these models were built in order to have this uptype Yukawa. Yeah.
Yes.
Now we have a uptype Yukawa. I mean, now of course one has to. I think Sakura told some people from Durham, they had some models on this, So I haven't been involved in any project involving real computation, but I think
Yeah, but my question is more what comes out generically in a SU5 F theory model for these Yukawa couplings? Because you seem to have to work very hard to get what you want, but that we can also do in other approaches.
Okay, this I'm not 100% sure. Okay. I mean, I'm just, somehow happy that somehow one cannot rule them out completely, So. Because it's after the Soliao paper seemed to be completely ruled out, So somehow we're still there, So I mean, what to do with them, I'm not sure. Sorry.
But after the Soliao paper, and then with this prime resolution, all the statements of alpha for computing Theta 1.3 and all those things, they have to be redone or something. Or? One thing is to get
I'm filmed now, So. I am filmed,
Okay.
Okay, I don't know.
So, can you get the point of E8, for example?
Sorry?
You have talked about E6 singularities.
Yeah.
Can you get E8 ones? Or is it?
Well, E8, I mean, E7, as I said, in order to get to get rid of the proton decay, I think E8 is, some extra. I mean, they wrote a paper. I mean, E8, okay, I'm not sure exactly why you go from E7. I mean, you go to E8 just to embed it in heterotic strings, for example. But there is some extra condition. There is a paper by Wafa and some collaborators 2 years ago where they explain why you need to go to E8. Yeah, sorry.
I have a question. There was this paper of Chicotti, Wafa, and Heckman on T-Bray.
Yeah.
What happened to that project?
Well, the problem is that then, I mean, everything I discuss here is, when phi is diagonal, so...
No, this is all, these T-branes to me looked a bit mysterious. You read the paper.
Yeah, I know.
They appeared all of a sudden, and now have they disappeared again, or because I haven't seen any follow-up of this. This
well, I mean,
picture.
yeah, I mean, the only
Is it
problem...
connected somewhat to what you?
No, I mean, okay, it might be connected a bit with, we thought a bit, but then we didn't really find it might be connected to these things here, I don't know. Maybe with T-branes you can get rid of this this square root, because here, you just have two entries on a 2x2 matrix, and then maybe if you put some extra diagonal terms, yeah. So it might be related, yeah. It might be related to getting rid of these terms, but okay, I don't have much insight on that, yeah. But it has, I mean, it has. This might be related to solving this issue, but I'm not sure.
So where are these T-branes?
Huh?
Where are they?
Well, T-branes is where, everything.
On T-brane, and it was written in such a way that it would solve the problem at all. I mean, it was probably 2 years ago or what?
Yeah.
It meant that in some cases, when you have matrices and you have this diagonal entries to break, sometimes you can have off diagonal.
Yeah. So it's like here, this field phi is diagonal, but then they claim that you might have, like this entry here, which is a 2x2 matrix with diagonal entries. You can have extra diagonal. Yeah. This is the T-branes.
So this was the statement that matrices can have off-diagonal.
Yeah.
No. And then,
I know.
I think there's also in the paper Weinhold.
Weinhold. Yeah,
He made
Weinhold.
the same remark.
Yeah, so
And
Weinhold.
now, this now becomes T-branes all of a sudden, and of course it's in a certain way bound states of branes and whatever. They even show pictures on some later page. But you see, now you would have thought that within 5 weeks you would have seen a few more papers on T-branes and using this technique to solve all problems.
Yeah, so Weinhold had told they resolved this equation for non-diagonal phi.
Yeah.
So, they resolved these Higgs bundles for
But
non-diagonal
even the
phi.
question what this geometrically is, what they call a T-brane, I think it did not become clear to me.
I think they gave some section in Donagi and Weinhold last year.
Again, Weinhold maybe,
Yeah.
but not in Chikoki.
No. I mean, it's, they just wanted to. I think the problem is with this
I guess
elliptic.
Donagi and Weinhold had the problem in somewhere. I don't know, earlier or later.
If I remember correctly, the problem was relating to this elliptical fibration, because when you take this elliptical fibration and you study the formation, then phi should be diagonal there.
Yeah.
So that was the
The
problem.
spectral cover in some
Yeah, and I think computing delta, the discriminant was hard for this, because this is where we kind of gave up. Yeah, we tried to do, but then we gave up because this discriminant of the singularity was tailor-made for diagonal phi, but then for T-branes was a bit difficult to obtain.
So this is related to the non-commutative thing, or is it different?
Well, it's related to the fact that when you have the spectral cover methods to go to the semi-local picture, that this might not be unique, that you can have much more freedom. Because in the spectral cover arguments, you usually have this kind of U1s, and you have some breaking down of symmetries by a diagonal matrix with vacuum expectation. That is when you do this desingularization. And there, when you have these off-diagonal elements, you have non-trivial solutions to this equation that might be different, so you might get to different semi-local pictures even, which give you more freedom, because you see these local models at a given point were known, at least the A model, to be inconsistent, at least with phenomenology. And then you say, okay, so what is the semi-local picture? What can we do?
Now they're going to the global pictures, no?
Well, the global picture, of course, is something which I think will be very difficult to do. It's like doing, it's worse than doing the Calabi-Yau freefalls for other fields.
Yeah, because the problem.
Calabi-Yau
Fourfold, yeah. So we don't have the I mean, there are techniques, but it's really hard work, so it's not.
Like going back to the whole picture, the whole.
Yeah.
And you see, there's not.
I mean, this is why this local F theory was kind of. I mean, it was simple, I mean, but unfortunately, it's really kind of small region, and
What about the other issues, gauge unification and so on? What is the status of that?
Well, I mean, all these developments were mostly the local picture and again, I mean, I'm not quite sure because so there was, I think, Marsano, Schaffer, Namek, and some Dolan, somebody from Durham, they developed some more phenomenology related to this.
And what is the conclusion?
I don't remember.
No, I guess the general picture of unification is that when you have these bundles, you have big threshold correction. Shevchenko and co-workers, they put in some additional triplets of SU5, which you separate tensor.
At low energies, triplets?
That's the energy which fits.
Which was how much?
Well,
The energy which fits.
no, even at rather low one. So, because the point is, this was actually pointed out by Blumenhagen in the simplest way.
That's this one,
When
right?
you have these bundles, there are these contributions which actually split. And then the nice thing was that when you look at the phenomenology, the precision phenomenology, actually, you know that the three couplings do not meet at one point.
Which is
So that is why
which
Wafa, when I
scale.
heard his
So you can
report,
change-
he predicted F theory to do it. The only problem is the sign is wrong. It goes in the wrong
It's
direction.
after the fourth term.
Is this the focus in business?
Well,
Yeah.
it was at the first time I heard him was at this meeting
Right.
in Philadelphia when
Right.
he explained it,
Yeah.
and then you see, then later I went to Pascos and there I met Stuart Rabi, and because he knew from Stuart Rabi that these were split, it was the 3% mismatch. And then I said, Stuart, yeah, they said, but you see, I told him that he was wrong, and then Wafa gave his talk in Parameter Institute at the Pascos, and there he no longer predicted the splitting.
Well, he predicted it in the opposite direction, in principle. If
Well-
the sign changed, that
The point is, it's also bigger. Then. So there is,
the sign changed and it's bigger.
no, the sign is opposite to what is observed in nature.
Yes. So that then you predict it in the wrong direction.
Okay,
right?
so,
But-
then at least he didn't call it a prediction anyhow. No, and the point is that in some way there is this discrepancy which you can actually resolve by putting in a pair of, or 5 pair of triplets, depending where you put the mass, you can change the number. And then they said this is actually very nice because we can use that for
But now you have
gauge mediation, supersymmetric.
Right, but the whole picture about then justifying the simple God theory disappears because you're putting
Yeah,
things
there is
on-
of course Weinhold and Bonagi claimed in the paper, of course, whenever such a thing happens, you can break the gut group in a more complicated way, introducing another parameter, and then you can solve the problem.
You can also.
I remember your discussion
No,
with
it's-
Stuart about it.
This was the thing in the
Okay.
simplest
Aren't you
case.
ashamed to do this?
I don't know
But
what
it's when you actually
How can you claim gauge coupling unification if you have an additional?
ask
parameter?
Wafa, ask all the people that claim that F theory makes these predictions.
And it doesn't work.
It's actually.
Given we're being filmed, shall we
Huh?
shall we take the discussion to
Yes.
lunch?
What